we will proceed with a joint presentation by André, Teles and André Santos on code merging using transformations and member identity.
All right. Good morning, everyone. Thanks for coming to the session. So we are both here. I'm going to start off, and then I will pass the word to the other André. So what are we addressing here? We're addressing three-way merge scenarios. You all know what is this, but just a recap. So we have a stream of software. At some point, someone branches. During the paper, I'll use the term left and right branch. So let's say we did a branch to the left, and then the original base keep on evolving, and we got the right branch. And we are addressing this process of getting these two left and right merged. This image, many of you should know, is from GitHub. So when we have a pull request, and we have the chance of merging it automatically, but we can get this message, okay? And why is this happening? It's because the two branches that are involved, the git merge algorithm is saying, okay, there is a conflict, so I'm not going to merge it. And because we'll get this result. Git merge uses text-based merging, and so the regions clash, and that's why we have this problem. And in the literature, this has been referred to as a false positive. Why false positive? Because this situation, in fact, you could merge the two methods in the same class, and that will not be actually a conflict. On the other hand, we might have a message saying, okay, yes, you can merge, but this doesn't come free from problems. Let me get another foobar example. So let's say this is our base class, and then the left branch renames the method foo, okay? The right one doesn't touch the foo, but adds another method in a different text region, okay? Git says there is no conflict, but in fact there is. If we try to merge, that foo reference is outdated, okay? And this has been referred in literature as a false negative, because the tool is not pointing out a conflict, but in fact, when we merge, we get not working software with compilation errors. Okay, now an example we will use during the talk. It's also very simple, but it will be hard to explain these things properly without a very small piece of code. So let's look at this very creative point class. Okay, let's say the base had this first version, 2 fields, 2 getters, no modifiers, nothing. And then the left version has added final modifiers, has added a constructor, renamed the getters to the get pattern, and added this isOrigin. Okay, very trivial. You can. And the right version has added different modifiers. There were no changes here, and also added some isOrigin, but using the original getters. Okay. When we go and merge this with git merge, so diff3, we get these conflicts, I'm afraid. Yeah, you can see like very light gray, which I see okay here, but in those regions you get some conflicts. I will point here just to be easier. So here we have a region conflict, and also down here. This is the same case as I showed before, so I'm not going to lose time on that. But then if we start applying research approaches, like for example JFST merge, which was published here at UPSLA, they do structured merging, so they are aware of the language structure, okay, but still at some points they cannot do a good merge. So for example here in the modifiers we have a clash, it's identified as conflict, and also here in the method body we have a clash. In another research approach, also published here at UPSLA more recently, IntelliJ, it does a similar job, so we also have conflict in this area, okay, but then isOrigin is not reported as a conflict, but the resulting code gives us compilation errors. So this X and Y are broken references, okay? So somehow the rename was not well handled. And we also run this case in JetBrains MPS. So MPS makes a model-based merging, okay, using the proprietary tool merge, using their models. And so here we got no conflict, but here still like it failed to see that these two is origin are in fact expressing the same thing, okay? We could also force, I had the idea, okay, let's force the case that MPS also doesn't work in the modifiers, but we didn't do it because it would seem that example will be contrived. But if we do like a static final, we also get a conflict up there, although those modifiers can be combined. Okay, so having this scenario, what we would like to achieve, so what we call the ideal merge, is this scenario. So everything, so all these changes are compatible and they can be merged into compilable code. This is what we would like to achieve, and that's what we can achieve with our approach. Okay, and so we're going to use this example throughout the whole presentation. But nothing comes for free, right? And one of the keywords of the title is identity. So what we mean by that, when we have classes and their members, we rely on a form of making some precise matching using universally unique identifiers. And our implementations, we did them as source code comments. So it's like the class and their members, they come with these comments attached, and that's the information we use to match, okay? For those you know, for example, MPS or back in the days, the intentional domain workbench, their models, they also have this sort of universal IDs to do the matchings. But here we are in a format that is still regular valid Java code that can be used with the regular tool chains. Regarding the other keyword of the title, transformations, so when we have changes, so for example, this branch, this version has evolved from the left side, we encode the transformation as the changes as a set of transformations. So for example, this one up here, okay, we encode this as a modifier remove in that element with a certain UID. The second one, we encode it as a rename method in the method insert UID. And this one is a new method in the class with a certain UID. So notice that this one is not yet with ID. Why? Because these IDs, they are not managed manually. They are injected once the class gets versioned. So once I first do a push to the class, that injects those IDs. And they are supposed to kept coherent as software evolves. This case we don't have because this will be a new method that is about to be pushed to the repository. All right, so now it's time to pass the word to André, which will explain like details of this merging.
Thank you. The first step of our approach is to parse the three versions of the code to an abstract syntax tree. After that, we extract the transformations between the left and the base version. As we can see, and André mentioned, we have transformations for the change of modifiers, the addition of the constructor, renames of the methods, and the addition of the method isOrigin. The next step is to repeat the previous step, but now between the right and the base version. And once again, we have less transformations, but we have the change of modifiers and the addition of a new method isOrigin. After obtaining the two sets of transformations, we check for shared transformations, that are transformations that are redundant. Okay, having these two sets of transformations, we can see there is the potential that the first two transformations might be redundant. However, as we have seen in recalling the two branches, one has final modifier and the other the private one, so they are different, they cannot be considered redundant. In addition, we have the add method isOrigin that also has a potential to be redundant. As we can see, their body is textually different, although we need to do a special parenthesis to explain how we handle body comparison here. Our body comparison starts by getting the UUIDs of the elements that the references point to. After obtaining these UUIDs, we replace the identifiers of the body with them. And as we can see, now they are textually equal, and we consider it to be redundant, and we factor out these two transformations into one new set of transformations, which we call the shared set. After obtaining the shared transformations, we start the conflict detection phase. So having these three sets, for each of these three sets and for each transformation in particularly, we check each transformation against the other transformations of the other sets. As André presented, we have no conflicts in our approach. That's why we have an ideal merge. But for example, if left would add a public modifier and right a private one, there is a conflict that needs manual intervention to be solved. Okay. Next, we have the merge process. Since there is no conflicts, we start by grouping the three sets of transformations and we rearrange it in a special way. We separate the addition transformations that are transformations that add new nodes to the AST, and the remaining transformations that are transformations that make modification to the existing nodes. We start by applying these addition transformations to the base version, but as we can see, we have broken references here with the addition of the new method isOrigin, because getX and getY are not defined in the merge version. So we do an intermediate step here that we have called the translation of identifiers by reference. That's the merge version we have, and we start by recalling what was the branch that originated the transformation isOrigin, the addition of method isOrigin, and that was the left version. And once again, we get the UUID of the elements that the references point to in the left version. We find the matching elements, the elements that have the same UUID in the left version to the merge version, and we apply their identifiers to the method isOrigin. After that, we continue the application of transformations, and we apply the remaining transformations in any order, but explaining special that the renames transformation, in particularly, rename also all the calls to the method or the element that is being renamed. Finally, after having the merge version in AST, we have to generate the source code based on this AST. Here's again the ideal merge with the UUIDs attached. Okay, we developed Jade, that is a prototype merging tool that has support to Java, but on recovering the more common elements in Java, methods, types, fields, etc. And it has 35 different transformation types, and is a prototype with around 6K lines of Kotlin code. Java parser is an essential library that we have used because it is used to parse the source code and also to make the necessary transformations. Okay, we also conducted an experiment to prove the feasibility of our approach. To our knowledge, there is no real merge scenarios that have any form of identity attached to them, so we had to fabricate ourselves. So we start by obtaining the merge scenarios from the material of the JFCT merge paper. We then find the matching files between the three versions by path. We parse them using Java parser, and we compute the matching element using GUM3, that is a code differencing tool. And to the matching element outputted by GUM3, we attach the same UUID to simulate that element was the same throughout the development cycle. We have obtained merge scenarios from two projects: Bucket, that is a Minecraft server API, and JSoup, that is an HTML parser. From the total of 63 merge scenarios, we had to exclude 6 of them in these 6 merge scenarios, at least one of the, or the left or the right set of transformations were empty, because the only modifications we had in that branch was in the elements that Jade was not covering. So we had to exclude them, because there is no point in doing the conflict detection phase when one side has no transformations. We split the results in 2 groups: the conflict-free group, which we aim to search for false negatives, and in a total of 43 merge scenarios, 34 have built successfully, but 9 of them had compilation errors. That happened because since we have in one of the versions, the left or the right, we had transformations that in members that are covered by Jade, but we also had some other changes that are not covered by Jade. And when applying only the transformations that Jade covers, created some broken references and the codes would not compile. However, since we did not find in these 9 merge scenarios, they all had compilation errors, not due a malfunction of Jade's implementation or a shortcoming in our approach. So we did not find any false negative. The other group, that is the conflict group, we have found 40 conflicts in 14 merge scenarios. We have checked each of these 40 conflict groups one by one to check if they were in fact real conflicts, and they were. They all needed to have some manual intervention to choose which version to apply. So we also did not find any false positive. Finally, we also explored the execution time. We have obtained around 3 seconds for bucket and 14 seconds for JSoup, in which 50% and 70% of this time respectively was in the parsing and indexing phase. We also tried to find a relation between the size of the project and the overall execution time. Bucket shows that they are linearly relationable, although in Jade there is something that is not so clear. Now I'll give the word again to André, so he concludes the presentation.
All right. So I will just wrap up by discussing some drawbacks and the respective benefits or workarounds. So you probably, when you saw the first slides about UUIDs, you're like, okay, so now the source code is going to have all that stuff. Of course, this is not ideal. First, because we have to see it, so it's verbose. And then also, because, most important, because they are fragile, right? If someone moves the method and doesn't come with a comment attached, there it goes, the UUID. So that's a problem. Okay, but possible solutions would be, okay, on a heavier scale, if we use projectional editors that completely hide that information, that problem gets potentially mitigated. But in a lighter version, we could just at least have some IDE plugins that fold those parts and you don't have to see them. And it's already an improvement, but the fragility will be still there somehow. Okay, so I think this could only be fully addressed with some sort of specialized editor, projectional or not, that really hides that information. Another criticisms could be like, okay, your implementation and approach is language specific to Java. So now if I need something to other language, I need to do all this stuff again. Okay, but being language specific also allows for more precision and some semantic awareness of the language. Okay, which modifiers can be combined? Does my language allow method overload or not? And all those fine-grained details, you can have more conflict detection or not in a more precise way. So the disadvantage is somehow an advantage. And then you also, if you compare those merge times with other papers, you can say, okay, it's a bit slow, 10 seconds, okay? But then, do we merge that often? And like having merged code with compile errors also takes a lot of time to fix. So if we take a bit longer, but we avoid less errors, that's a good thing, and we can live with the 10 seconds. So I don't think that's really an issue if we improve the other side, right? And yeah, so we managed to do proof of concept with more precise merges, so less false positives and less false negatives. And that's future work. We envision, so we don't approach this in the paper, just in a speculative form. So improving JADE coverage, that would be an obvious improvement, and this is doable. Like, for example, we don't cover things like the static initialization blocks or methods inside the enum constants. You know, these little corners of Java, for pragmatic reasons, we just focus on the essential. So we could improve here, and that's feasible. In a more, in another aspect, so we just discussed the happy path that we have the ideal merge. We kind of skip a bit the conflicts, because we envision that once we had a set of transformations that is not compatible, we could have a tool that helps the developer to select among alternatives. Of course, this will not solve all the things, but sometimes, you know, someone renames the same method with different IDs. This requires manual intervention, and then one could go there and select which version he or she wants. And yes, we'd also like to test this with people, okay, and especially this part of conflict resolution, to see how that could be handled. Yes, and we are happy to take questions. Thanks.
We have time for several questions.
Thank you for the nice talk. It's an old school topic that is still hot, I would say. So you addressed this challenge that let's say the textual representation and the models you want to difference and merge, they are not in the same world. So, because the text lacks stable identity. Yeah. So could you store them in a table outside of the source code, since programmers don't like to see that in their source code?
Yeah, we got that comment in the review, actually, if we could use some sort of external stuff. But aren't they still fragile anyway, or?
I don't know. Yeah. I guess if you have a source code location table, your editor can then help you, and then at least it will be sort of transparent, and maybe your algorithm can perform better when this information is available, and when it's not available, it falls back to the inaccurate behavior. Yeah, I agree with your suggestion, but we really didn't, sit down and think how could we do this as an external representation. The source code was mostly like let's say the most obvious way to attach things, and it was a bit pragmatic. Okay, we didn't explore much there. Yeah. Thank you.
Welcome.
Other questions? So a question from my side. So you mentioned reducing or having fewer false positives and false negatives. What were you comparing against with that statement?
Okay, Tricky, do you want to answer this one, or?
I can answer it. So we did not compare our approach with other approaches, false negatives or false positives, because there are some, just a moment please. Sorry. Okay. Here, as you can see, in many approaches that we have presented, we have, I would say we have different granularity of conflicts. I mean, in the Git merge, as you can see, the bracket is inside the conflict. But in the JFCT merge, it has, the conflict is more localized. It's between the method, its origin. And it's difficult for us to compare to other approaches because we don't have this format of showing conflicts. we can have 3 conflicts or we can have 1 conflict. And for example, we only have 1 body transformation. We can change a lot in the body, but it's only 1 body transformation. When in other approaches, if the body of the method is so long, we can have different conflicts, it's localized. So we didn't find it's always useful, but it's hard to compare our approach when the body has a single transformation and then has a single conflict, and when other approaches in a long method have 1, 2, 3 conflicts.
Yeah, it's like the unit of measure is not the same. But when we claim that we have less false positives and negatives, we are showing situations that the tools don't handle. So it's these ones we are reducing. We could not do like a thorough comparison.
But would it be possible to argue that you don't introduce new false positives or false negatives?
Yeah, that's what we tried to see in the study, to see if our thing was not doing that, and no false positives, right?
Yes, no false positives and negatives, because we think that having a large database of conflict types between pairs of transformations and that is well implemented would avoid false positives, because it has a list of rules that the members have or not. And also about the false negatives, the application of the transformations, when well applied and well implemented, the application of transformation, that should not introduce any compilation error, at least syntactically. Semantically, it's a whole world.
Final question from my side. So you mentioned being specific to a particular language with your implementation. So maybe you can reflect a little bit on the sort of the key insights that would transfer to other languages.
Yeah, maybe I can take that one. Yeah. Okay, the idea is portable. The implementation not, because for example, so we parse all the Java. We have this Java-specific nodes, and some things in the details is where. The detection goes into the details. Okay, so of course all methods have all languages have functions and methods, so on. So that's the easy part. But then, for example, if you do this for JavaScript has no overloading. So in our case, if we see one branch has one method, the other with the same name with different signature, that's okay. It's compatible. But in JavaScript, that stuff would be a conflict because it's not allowed. So it's those kind of the devil is in the details. So, but the whole approach, I don't see any. Why shouldn't this be portable? The idea, not the implementation. Okay.
All right, please join me in thanking the speakers again.